Hi, this is Sebastian and I will present our work SGRec3D, Self-Supervised 3D Scene Graph Learning via Object-Level Scene Reconstruction. 3D scene graph prediction is the task of going from a 3D scene reconstruction to a 3D scene graph. This step can be performed using a neural network which takes as input a 3D point cloud and outputs a graph representation where predicted nodes represent objects and edges represent relationships between objects in the scene. To predict the 3D scene graph, the network is trained in a supervised manner on object and relationship labels present in 3D datasets. However, compared to object annotation in 3D datasets, there are no large-scale relationship labels for 3D scene graph learning. Therefore, the goal of this paper is to propose an approach to learn 3D scene graphs more efficiently using self-supervision, and to utilize larger 3D datasets for 3D scene graph learning. To this end, we propose SGRec3D, a self-supervised pre-training approach using a 3D scene reconstruction task. We propose a novel scene graph encoder-decoder based approach with a novel scene graph bottleneck. Using this approach, we are able to pre-train a latent graph representation that can be used for 3D scene graph prediction. This approach introduces two major advantages for 3D scene graph learning. First, the network can be trained without any scene graph labels, and second, this makes it possible to pre-train our network on a large-scale 3D dataset, such as, for example, ScanNet. To predict 3D scene graph labels, we can then fine-tune the encoder part of our network on a comparably small dataset to predict 3D scene graphs with the desired object and relationship labels. In detail, our approach uses two point nets to construct an initial feature graph from the 3D point cloud. This initial feature graph is then processed using a graph neural network into a latent feature graph that contains not only local object features, but also propagated contextual features. The latent graph is then decoded using another graph neural network, and we predict bounding boxes and shape encodings from it. We predict shapes and boxes separately rather than predicting the full 3D point cloud all at once, which is challenging because of the large-scale and non-continuous nature of the 3D point cloud. As a reconstruction loss, we propose a self-supervised bounding box L2 reconstruction loss and a shape encoding L1 distance loss to a pre-trained AtlasNet encoding of the object in the scene. AtlasNet is a 3D point cloud autoencoder for single objects, so training on its shape embedding vector distills the knowledge about 3D object shapes into our network. To predict full 3D point cloud reconstructions, we can then decode our predicted shape encodings using the decoder part of the pre-trained AtlasNet to predict object point clouds, which can be placed within our predicted 3D bounding boxes. To fine-tune our method for 3D scene graph prediction, we discard the decoder and fine-tune the encoder part on a small dataset with two weighted cross-entropy losses for nodes and edges. Here, we present two exemplary 3D scene reconstructions from our method. We observe that the reconstruction quality is not super high. However, more importantly, we observe that object relationships that are present in the original point cloud are still present in the reconstructed point clouds. For example, those pictures hanging on the wall are preserved to be hanging on the wall in the reconstruction. We reason that the preserved relationships in our reconstructions are a good indication for the learned relationship knowledge during our pre-training. This observation can also be shown quantitatively. In this table, we report the reconstruction accuracy of our method for relationships where a simple rule can be approximated. We observe generally high accuracy in the reconstructed relationships for all evaluated relationships. Here, we present two predicted 3D scene graphs from 3D point clouds using our method, with correct predictions highlighted in green and incorrect predictions highlighted in red. Overall, the majority of objects, as well as relationships, are predicted correctly, even with detailed class descriptions as couch table or very semantic relationships like standing on. Our pre-trained approach achieves state-of-the-art results when compared with recent 3D scene graph baselines that were all trained in a fully supervised manner. We evaluate the individual object predictions as well as the individual predicate predictions as well as a combined relationship prediction of a subject-predicate-object relationship using a top K recall metric. Furthermore, our pre-training approach is especially effective for rare tail-end classes where we see the largest quantitative improvement over the baseline non-pre-trained approach. Our method is the first approach for pre-training a 3D scene graph network. However, we ask ourselves, how does our pre-training approach compare against other modern point cloud-based pre-training approaches? Here, we report the object and relationship prediction performances on two different object and relationship metrics for a model without pre-training. Here, we report our model pre-trained with the recent point cloud-based pre-training strategy, SGRL. We observe that this pre-training improves object prediction, but does not improve relationship prediction or actually decreases the relationship prediction performance. The same can be observed for depth contrast, another recent point cloud-based pre-training approach. In contrast, our approach is not only effective in improving object prediction, where it improves results even further than SGRL or depth contrast, but due to its tailored scene graph-based pre-training, it is also effective for improving relationship prediction compared to our base model. Since our proposed self-supervised pre-training approach does not require scene graph labels, we are able to pre-train our scene graph model on a larger set of 3D datasets. Pre-training on more data drastically improves our prediction results for objects, predicates, and relationships by several %. Also, our pre-trained approach is much more efficient when only a limited number of labeled data is available compared to the non-pre-trained method. We observe that even using only 5 to 10% of labeled data samples during fine-tuning, it is already enough to match or even outperform the non-pre-trained approach trained on all available labeled data. This concludes the overview of the SGRec3D, a novel pre-training approach for 3D scene graph learning that considerably improves 3D scene graph prediction. Please follow the link below to the paper and project page. Thank you for watching this video.